So it is visible and audible?
It's not audible, but it's visible.
This is visible.
It's not audible.
No, sir. I think you have to join with your audio.
No, it's not. This.
Yes, yes. You are audible. अच्छा. Okay. Mm-hmm. अच्छा. An actual video from. No. Video is running from your side. Probably Probin sir.
हेलो सर. सर यहाँ पे ऑडियो तो ऐसा कुछ है ही नहीं ऑप्शन. नहीं सर, कोई तो ऑप्शन नहीं आ रहा. हाँ हाँ हाँ. हाँ नहीं, ये तो कुछ ऐसा कुछ नहीं, सिर्फ शेयर के बाद फिर डेस्कटॉप पे सेव ऑप्शन आ रहा है, और तो कुछ ऑप्शन नहीं आ रहा. अभी मैं से डेस्कटॉप शेयर किया. हाँ, उसके बाद अगर मैं भी फिर से करके देख रहा हूँ. इसमें तो नहीं आ रहा. हाँ सर, कुछ भी तो नहीं आ रहा इधर. हाँ हाँ, स्क्रीन वन टू, हाँ इंटायर स्क्रीन. कुछ भी नहीं यहाँ पर, शेयर कुछ आ ही नहीं रहा. शेयर के साइड में नहीं, कुछ भी नहीं आ रहा. ऑडियो तो आ रहा पूरा, लेकिन आ रहा.
Or end?
मतलब वो कोई और चला सकते हैं क्या? सर
Divya sir? Praveen sir? Sir, am I audible?
हेलो.
Praveen sir? Praveen sir, I think you just play it. Uh, Audio is not there, but let us just play it. We'll start at 4 o'clock. The more students will join. Many research scholars are trying to join because the topic is very interesting and something that they really are using. So let us start, sir, and students will join, sir.
Okay, it's okay. So am I audible? Hello ma'am, am I audible? Hello ma'am. Hello. Hello ma'am. Hello, ma'am. Hello, Dhananjoy sir.
Yes, yes, Praveen sir. Your sound is audible.
Okay, good afternoon, all. So I am Praveen Kumar Sharma, Assistant Professor in the Department of CSE, IITR, SOA. So I welcome you all in the weekly academic series, lecture series of our university, which is held by the Department of Computer Science and Engineering. I welcome our HOD, Dr. Bhakta Mishra. And it is very pleased to inform you that we have successfully conducted 52 webinars in the previous academic year, that is 2021 to 2022. Okay, in this academic session also we are conducting the lecture series, that is Soawal-Cse 2. So, and today is the 14th lecture series of the Soawal-Cse 2. So today we have Dr. Dhananjoy Bhakta, Assistant Professor in the Department of Computer Science and Engineering, IIIT Ranchi. Okay, so before we start the session, I want to play a 5-minute introductory video of our university. So just be with us. After the video, we will start our session. So before we start the session, let me introduce our today's speaker, that is Dr. Dhananjoy Bhakta. So Dr. Dhananjoy Bhakta has received his BTech degree in Computer Science and Engineering Department from the West Bengal University of Technology, that is in Kolkata, in 2006. And he done his MTech degree in the same Computer Science and Engineering Department from the National Institute of Technical Teachers Training and Research, that is in Kolkata, and in 2011. He has received his PhD degree in the Department of Computer Science and Engineering from the National Institute of Technology, Durgapur, in 2017. So, and currently he is working as an assistant professor in the Department of Computer Science and Engineering in the Indian Institute of Information Technology in Ranchi. His research interests include pattern recognition and machine learning. So I would welcome Dr. Dhananjoy Bhakta to enlighten us with the topic, that is support vector machine and with its applications. So over to Dr. Speaker.
Thank you, Dr. Praveen. Very good afternoon to all. Join this meeting. First, I would like to thank the Computer Science and Engineering Department of SOA University, and I thank you to this webinar program coordinator, Dr. Praveen Sharma. Now today, in this topic, weekly webinar program, I just want to discuss very briefly support vector machine and its applications. So, may I share my screen?
Yes, sir, sure.
So let me confirm the screen is visible.
No, currently it's not visible.
Hello.
Yes, sir.
Yeah,
Sir,
please.
The screen is not visible.
Sir, it's Praveen, sir. I am able to see.
Okay, it's not visible to me. Vishnu sir, is it visible? Anyone else can confirm?
Yes, sir.
Okay.
Julius,
Okay.
can you?
Yeah, anyone? Any of the participants?
Julius, can you confirm if it's visible, Divya, sir? I can see, so I think it's working. I think there's something
Okay,
wrong.
it's working then.
Okay. So in this today's topic, the content mainly covered introduction, very basic of machine learning and some learning techniques involved in machine learning. Then supervised learning, support vector machine, that is hard support vector machine, soft support vector machine. Then kernel function or kernel trick used for solving nonlinear problem. Then properties of support vector machine, then applications. Now, before starting support vector machine, we need to know basics of machine learning. What is learning through machine? Now, learning is the process of acquiring knowledge from the environment and perform some specific task according to knowledge gained. And there are different learning rules applied in the machine learning. Depending on the nature of learning, weight adjusting process for attaining optimized value. Everything in machine learning we have to optimize. That is the learning techniques can be broadly categorized as 3 different types. One is supervised learning, that is mainly task driven, because we have provided input along with its output, that is label. So labeled data will be used for supervised learning. So this is task driven. So data and task is available to us. Next is unsupervised learning, that is data driven, completely data driven. No task is assigned, that is unlabeled data is given to us. So we have to identify the level based on some similarity measurement. Then third kind is reinforcement learning, that is learned by mistake. So each of these learning technique use different learning algorithms, and I mainly discuss this supervised learning because this is the scope of this topic. Now, supervised learning mainly formalize the idea of learning from examples, because we have given 2 sets of data, that is training sets and test set. So learner, a typically computer program that is learning provided with these 2 sets. One is training set, that is learned from a set of labeled examples, and so that it can test or identify unlabeled examples that is not present during the training with the highest possible accuracy. So goal of this learner is to develop a rule, a program, or a procedure that classify a new examples during testing. So there are many different approaches that attempt to build the best possible method to classifying examples of the test set by using data given in the training set. Now, in supervised learning, there is a teacher or supervisor is present to provide a desired output for each input who has knowledge about the environment. For example, if I mainly x1, y1, so for input instance x1, y1 will be the correct output. So output will be the provided along with this input. So there will be some teacher or supervisor who will guide you. That is y1 is the corresponding output for x1. So now come to the support vector machine. Support vector machines are mainly used, that is most popularly used machine learning algorithm for classification purpose. Although we can use it for classification as well as regression purpose. And one more thing about supervised learning, there are 2 kinds of tasks performed by supervised learning. One is classification, another is regression. So when the value is not numeric, then we can perform classification. So classification, that is assigning class level, predefined class level to an unknown instance. So it can be used for support vector machine, can be used for classification as well as regression or regression estimation. So this support vector machine, why it is required? When we don't have enough data set to implement artificial neural network, because we know that artificial neural network is most popular for classification, most popular machine learning approach for classification. But when the data sets are limited, so there is not much enough data set to implement artificial neural network, then we can use support vector machines. Now, a classification problem, I already said this support vector machine is linear classifiers, but a classification method, this support vector machine can be used for both linear as well as nonlinear data by applying some kernel strategies. So by using kernels, all computation is simple. So this linear classifier also can be applied to the nonlinear classification with the nonlinear data. So it uses nonlinear mapping to transform the original training data into a higher dimension. That is I will discuss this in details when how we map this nonlinear data. Now with the new dimension, so higher dimension, that is we have to transform lower dimension to higher dimension, so we have to add some new dimension. So with the new dimension, it searches for the linear optimal separating hyperplane, that is called decision boundary. So with an appropriate nonlinear mapping to a sufficiently high dimension, data from two classes can always be separated by a hyperplane. Now SVM find this hyperplane using support vectors. Now why this is called support vector? Because this supports the solution. Support vectors, these are the main component of support vector machine. So support vectors, what is support vectors? I will discuss. So support vectors supports the or contributes to the solution. So if we delete non-support vectors, then the result will be the same. So and margins. So we have to find out the support vectors and margins that defined by the support vectors. So if we go back to the history of support vector machine, that is it mainly borrowed the concept from the statistical learning theory that was developed in 1960s. So what statistical learning theory is, that is mainly whatever we use in supervised learning, that mainly understood by the statistical learning theory, because statistical learning theory involves learning from a training set of data. So the learning probably consists of inferring the function that maps between the input and output from feature input. So support vector machines were originally proposed by the Bozar, Guyon, and Havnik in 1992 and gained popularity in the late 1990s. So VC dimension, why it is required? This is Havnik, Sarbonenkis jointly developed this dimension because they consider a set of member of the set function f of alpha, and that can be found which correctly assign the level for all levelings. That is they can be set at all points, whether it belongs to positive side or negative side. When we are talking about two class problem, then either that will be the negative or positive. So this f of alpha, that is VC dimension of f of alpha, will be shattered the training maximum number of training points. So here we can see that 3 points are shattered by f of alpha. So here we can use we use only 3 points. There can be many points, but there will be some problem when use VC dimension. Now, if I give this type of example, okay, say there are two class 1 and class 2. Now, how we divide this? So how would we classify the data? If you are familiar with perceptual learning, then you can use any hyperplane between these two data set. Okay, so using perceptual learning to learn W, weight and bias, and with different initial values of W, and that is W, weight and bias. So with different set of W and bias, and what happened? We will get a different hyperplane. So the question is, this will leading to the many decision boundary in the next. So many decision boundary can be obtained. Now, this problem does not, SBM does not suffer this problem. Okay, so SBM choose the optimum one. Now, here you can see which classifier will be provide the best result. Class 1, class in figure 1, in figure 2, or in figure 3. So this is the main question of this solving this problem support vector machine. So we can see that several decision boundaries can separate these two classes, and one popular technique used for this, that is perceptual learning algorithms that separate any and find the optimal value of W and B. But SVM learns the best separating hyperplane. Now here we can see that the figure 3 will be the best hyperplane in the figure 3, because we can see that data points of the class 1 and data point of the class 2 will be almost equal distance from the hyperplane. Okay, so this distance and this distance almost same. So if why this is required? If we add due to some noise, say this is noise is here. Okay, this is noisy version of this data is this. Now, if I consider the second hyperplane, then the data point will be misclassified. So this will be, this hyperplane will be it's optimal, should be optimal. So we require this optimization. Now there will be several hyperplane can be drawn by this. Okay, by using the perceptual learning algorithm. Now, the main task of support vector machine is maximize the margin. What is margin? This margin. Okay, this is one hyperplane, say hyperplane H1, and this is another hyperplane, say H2, and we have to maximize this margin. So how we maximize this margin? Define classifier as the width that the boundary could be increased before hitting a data point. So we just, if we rotate this line and we get the optimal value. So here you can see margin will be maximum for this example. Okay, and the points close to the or on these two hyperplane will be the support vectors. So if we delete all the other points except the support vectors, then we will get the same result. So this is very important, and this mainly contributes the to the solution. So this will be the hyperplane that is optimal. Now, why maximal margin? I already told that better for future prediction and reduce error rate. So misclassification rate will be reduced here due to some noise. If so, Now I discuss some mathematics behind this support vector machine. So how we achieve this equation Wxi plus b. Now let the set of training examples D be x1, y1, x2, y2 up to xr, yr, and xi is x1, x2 up to xn is the input vector, and yi is the class level. So the class level is 2. There are 2 class. I just solved this problem for 2 class because this is SVM mainly used for binary classification. We can convert it into multi-class classification, but using the binary class classification. Now yi belongs to 1 and minus 1. So 1 denotes, that is plus 1, positive class, and minus 1 denotes the negative class. So now, so this point Wxi plus b, if it is greater than or equal 1, then that belongs to positive class. The point, this xi data point belongs to positive class, or Wxi plus b less than equal 1, then that will be the negative class. Xi will be the negative class. In general, for all I, we can state that yi Wxi plus b greater than equal 1. So whatever positive class or negative class, we can say for correctly classified. Here I mentioned that for correctly classified all training data, this constant should be hold. Okay, so yi Wxi plus b, that must be greater than equal 1. So here we can see if this xi belongs to negative class, so this is value of this is negative, minus 1, and so this is also negative, that is less than equal 1, minus, so minus multiplication positive. If this is plus 1, this is also plus 1, so this is also 1. But if it is incorrectly classified, then minus 1 and plus 1, so this constant should not be hold here. Okay, so this is for correctly classified training samples. Now for 2-dimensional, it can be written as W0, W1 x1, W2 x2, if x1 and x2 are the 2 different dimensions. So the hyperplane defining the sides of the margin, we can formulate this h1, that is W0 plus W1 plus x1 plus W0 plus W1 x1 plus W2 x2 greater than equal 1 for all positive class, and W0, okay, in the last slide, probably this one. So W0 plus W1 x1 plus W2 x2 is less than equal minus 1 for all negative class. So any training samples that fall on hyperplanes h1 or h2 are support vectors. Okay, so here we can see examples on the hyperplane, that is this red circled data points, this blue circle data point, these points will be the support vectors. So Wx, and this will be the Wx plus b, this line, this will be the middle of this h1 and h2. So we can denote it by Wx plus b, and this will be, I just in the previous slide you can say that is Wx plus b, this you can assume this is b, Wx plus b is greater than 1 for h1 if that is positive class, and for h2 Wx plus b less than equal minus 1. Okay, So here you can see that this part wx plus b greater than 0, that is if it is greater than 0, then it will be in positive class, and if it is less than 0, then it will be negative class, and if it is equal to 0, then on the hyperplane. So if the point is in this plane. So this way we find the margin M. How we obtain this margin? We can obtain this margin in this way. You have to find out this, say this is your 0, 0 origin, and if you say this is your Q, and this is P, and we have to obtain Q minus P as a margin. Okay, so whenever I find this Q point, so Q will be Wx mod of Wx plus B, and it is positive class, so minus 1 divide by norm of W. Okay, so and we also find the P as Wx plus B plus 1 mod of this divide by norm of W. So if we subtract Q from P, we will obtain this margin. So the decision boundary or hyperplane should be as far away from the data of both classes as possible. So we have to maximize this margin in support vector machine. So we the main task is we have to maximize this margin M, or this is also same as minimize this half of W transpose W. Okay, we just reverse this. So if we have to maximize this margin M, then we have to minimize 1 by M. So this is 1 by M. Okay, and we can formulate a quadratic optimization problem. Quadratic, why quadratic optimization problem? Because this is a constant optimization problem. So we have to solve this W, that is weight, and B bias. Phi of W is equal, we have to minimize phi of W equal 1 upon 2 W transpose W. So, and subject to constant is yi Wxi plus B greater than equal 1 for all I. So this way we have this is the main logic of support vector machine. We have to maximize this margin, and after maximizing this margin, we will get the decision boundary. That will be the optimal hyperplane. Now, what if the training set is noisy? If training set is noisy, then what happens? Say training set, if training set, this is a training point and some noise is occur in the training set or some other noise. So then what will happen if there is some noise? So till now we have talked about hard margin classifier. Hard margin, that is only apply for linear data set. Now we will discuss soft margin classification Now, if the training set is not linearly separable due to noise or some difficulty, misclassification or difficult, so we just allow additional variables, that is slack variables. We just allow additional variable, that is slack variable psi I, to allow misclassification of difficult or noisy examples, resulting margin called the soft margin. Okay, so we can extend the concept of hard margin classifier to solve data set with outliers. So due to outliers, the problem can not be solved by linear separating plane. So all data points in real life, we know all data points cannot be separated using a straight line, simple straight lines. So there will be some misclassification, and if we familiar with regularization in regression, so this is just similar to regularization apply in the regression. So if not linearly separable, we just allow error psi I in classification. So here we can see this, and there are two cases that instance may lie on the wrong side of the hyperplane and be misclassified. Okay, that is this xi. Okay, so there will be two cases. One is instance may lie on the wrong side of the hyperplane and be misclassified due to some noise, and instance may be on the right side but maybe the margin, maybe in the margin. So here we can see this is within the margin. Okay, so not sufficiently away from the hyperplane. So for this we just introduce this slack variables, that is psi I or psi j here psi I. Okay, so which store the deviation from the margin. Okay, this is deviation, how much deviation or how much error we can allow. Okay, so this is nothing but this is just trade-off between finding a line that maximizes the margin and minimizes the misclassification or misclassification. Now, so just a formula will be changed in this way, so we can reformulate with this psi I. Some problem? Hello.
Yes, hello.
Is there any problem?
No, no problem. It's audible.
No problem. Good.
Okay. So define this slack variable. If we take this slack variable is to 0, that is no error for xi. So just we can reformulate the previous equation of support vector machine, that is W transpose xi plus b greater than equal 1 minus psi I, and in case of negative class -1 plus psi I. So this psi I is greater than or equal 0. Now if this is 0, exactly 0, then this xi data points will be classified correctly because there are no error. Okay, now if this slack variable lies between 1 and 0, then xi is correctly classified but in the margin. And if it is greater than 1, then xi will be misclassified. So we want to minimize this half of W norm. We just taking this square because this is this W term is square root, that is square root W1 square plus W2 square plus up to Wn square in n dimensional. So half of half multiply W norm square plus C. C is the controlling parameter because this is the trade-off between trade-off parameter between error and margin. And this is just a tuning knob. By controlling this, we can reduce the concept of overfitting and summation over I1 to n psi I. So optimization problem becomes minimizing half W norm square plus C summation over I1 to n psi I. So this subjected constant is subject to yi W transpose xi plus b greater than equal 1 minus psi I. Just change 1 minus psi I. So we have to subtract the slack variables. Now the condition for C. What will be the condition for C, and how this C controls the overall error? That is, if the value of C, we are taking the value of C is very small, then that will be results in a wider margin and at the cost of some misclassification if it is small. And if it is large value, then this that will be just giving you a hard margin classifier. So C, this controlling parameter can be viewed as a way to control overfitting, and it is the training. It is the trade-off, the relative importance of maximizing the margin and fitting the training data. So how we this problem can be fitted into the your training samples. Now Lagrangian trick. Why we should take the Lagrangian? Because in mathematical optimization, the method of Lagrange multiplier mainly used to find the local maxima and minima. So we while we maximize the margin, so we require this Lagrange multiplier. Okay, so reformulate the optimization problem, do an Lagrangian formulation of the problem, and constant will be replaced by constants on the Lagrangian multipliers. So here we just take the alpha Lagrangian multipliers. So we take L of W weight, B bias, that is biasing. This B control the position of the hyperplane, and alpha is the Lagrange multipliers. So we just put this formula, half W, we can write it W transpose W or W square, summation over I1 to m alpha I yi W x plus b minus 1. So this is the Lagrangian. If we convert this this problem to Lagrangian form, so we just write this. Now we solve this problem. Now we have to optimize this Lagrangian where alpha is the alpha is the Lagrangian multipliers. Now you can say write this alpha I. Okay, this is alpha I, alpha subscript I. Now we are taking the partial derivatives over B and partial derivatives over W. So when we are taking partial derivatives over B, we just write it down. Del of del B. So half W multiply W minus this first term. Okay, so that is summation over I 1 to m alpha I yi w x. This is xi. Okay, one term, and minus summation over I alpha I yi and b minus summation over I alpha I. Okay, so whenever when we take these partial derivatives over B of this L, we will obtain, you can see that this is independent of B, this is also independent of B, and only this part will remaining. So we just taking these partial derivatives and equate it to 0. So this will summation over I alpha I yi is equal 0. So that implies summation over alpha I yi is equal 0. So this is one term with respect to B, and another is, so you can see that this one is you obtain W by taking partial derivatives over this W minus you get this, that is summation over I alpha I yi and xi, and equate this to 0. Okay, so because we have to maximize the B and minimize the W, so this implies W is equal alpha I yi and xi summation over I. Okay, so here you can see this is vector. Okay, so because this alpha I is a scalar, this yi is scalar, but xi is the vector, so this will be not the dot product. Now we put these two expression of into the original Lagrangian formula. We will obtain, if we just put this to original, so what is that? L equal minus summation over I alpha I yi b minus summation over alpha I yi W dot xi plus summation over alpha I. So this will be equates to 0 because alpha I yi is 0, this part 0. So this will be 0, and we obtain alpha I summation over alpha I minus this. You just replace this by summation over I, and this is half. Okay, you just replace this, that is alpha I alpha j. We are just taking 2 subscript because this w dot this w. Okay, so dot product are here. So alpha I alpha j yi yj xi dot xj. This is dot product. Okay, so this will be the resultant. So here you can see this is independent of w, and this is only depend on the alpha I, that is the Lagrangian multipliers. So this formula alpha I minus half summation over ij alpha j yi yj xi, this will be the dot product. So we need to see xi xj input vectors appear only in the form of dot product, and we will soon see why that is important. Because when we apply this in the nonlinear solving nonlinear problem, then that will be useful. Now, how we test the, this is your training part is complete. Now, this is the testing part for classification of unknown feature vector z. So we are taking d of j equals sine of summation over I1 to m alpha I w I alpha I yi xi multiply z. This is the w. So w dot z plus b. So you know this, and you have to calculate this margin or bias b 1 upon 2 minimum for all positive class summation over I for all positive class y belongs to all positive class alpha I yi xi xj plus maximum of summation over I for all negative class y belongs to all negative class alpha I yi xi xj. So only sign is required. Okay, if the sign is positive, then z will be in the positive class. Here I assume that class 1 is positive and class 2 is negative. So if the sign is positive, then z will be the positive class, and sign is negative, then class will be the negative. So only sign is the important here. So next, nonlinear hyperplanes. Now, if the nonlinear separability is not caused by the noise, in the previous section I discussed due to some noise, we just add slack variables. Now, if the data are characteristically non-linearly separable, say we have two images and that two images are non-linearly separable, that is that cannot be separated by a line, straight line for two-dimensional case. So we have to project our data from a lower dimensional state to higher dimensional state. So for this we require, here you can see this data is belongs to one class, this data is another class, but this two class cannot be differentiated by a hyperplane. Okay, straight line here. So if we can higher the dimension, say this is your 2 dimension, and you just add one more dimension, that is 3 dimension, and in the 3 dimension this will be the so in 3 when we extend dimension, then that will be the problem will be solved. So mathematical solution to determine the hyperplane, that is the use of kernel function. So when no clear boundary is found or soft margin does not help, so after introducing slack variable, the nonlinear problem will not be solved. If then we can use the kernel function that to extend a linear SVM to a nonlinear SVM, and kernels that have a very high dimension can result in a support vector machine overfitting the data. So if we take the kernels and if we choose the kernel that convert a lower dimension to very high dimension, then that can be result in the support vector machine with the overfitting of data. So in reality, kernel function directly works on the dot products of data points in a new feature space. And here you can see the first case will be solved. So we just take this margin, but what about this? So we cannot take this margin because we can see this is one dimensional. So if we can convert this into 2 dimension, then the figure will be like this. So in this case, we can differentiate. Okay. So there are common support vector machine basis function used, that is linear k of xi xj. So instead of using just dot product of 2 features, that is xi and xj, we are just taking some kernel function, that is k of xi comma xj. So that will be some simplified logic. So this is linear. Second is polynomial kernel function, that is 1 plus xi xj to the power p. P is the degree. And if I can use, that is radial basis function. So this is just similar to radial basis function neural network. And exponential of minus, this is the Euclidean distance between xk and cj. Cj is the mean and xk is the feature, and sigma square is the spread variance. So the feature space is infinite dimensional here. And in the fourth case, we can use the sigmoid, that is the tan h function. So different kernel function mainly used for different purpose. For text classification, there will be some fixed kernel, and for image classification, there will be some other kernel. So we just apply the Lagrangian formula after applying the kernel. So we know this equation, we just derive this equation, and here we know that this is the dot product because this is a vector, this is also vector, but these all are scalar. Alpha I, alpha j, yi, yj is scalar. So this is dot product. So the data points only appear as inner product, but we can convert this in this way, that is phi of xi, phi of xj. So we just transform lower dimension to higher dimension here. For example, we can check, say we are just taking x1 and x2. Okay, this is 2 dimension, but we just add, if we perform squaring, then we will get this, this is shift operator, just shift by 1, and x1 is this feature, x2, and squaring this term, x1 square, x2 square, and x1 x2. So we just convert this inner product into 5 features here. So x1, x2, x1 square, x2 square, and x1, x2. So dimension is 2 dimension to it is converted into 5 dimension. So there is some we can choose this kernel function, and this is very important part. How we choose this kernel function and what kernel function will be suited for this type of problem. There are different properties of support vector machine. That is 2 key concept of support vector machine. One is maximize the margin, another is kernel trick. So tuning support vector machine remains a black art, and selecting a specific kernel and parameters is usually done in the try and see manner. So flexibility in choosing a similarity function, sparseness of the solution when dealing with large data sets. So only support vectors are used. So we require less memory, because if we store the support vectors, we don't require to store every other pattern, other inputs. Okay, so these support vectors mainly decide the solution. So ability to handle large feature space, complexity does not depend on the dimensionality of the feature space. So overfitting can be controlled by soft margin. I already discussed by using of C, and that is tuning knob, and psi I, that is slack variable, and nice math property. So applications, support vector machines mainly best performance because it's performance in terms of accuracy. So highly accurate. Support vector machine can be applied to complex data types beyond feature vectors. By designing kernel function for such data, support vector machine techniques have been extended to a number of tasks such as regression. So we can also perform regression problem, but mainly used for classification because it's higher accuracy. Or principal component analysis, these are the research scope. Support vector machine is useful for alternative to neural networks where data sets are limited. So mainly successfully used in real world problem like text categorization, image classification, bioinformatics, that is protein classification, cancer detection, handwritten recognition, 3D object recognition, speaker identification, regression estimations, or functional learning. So different advantage and disadvantage of support vector machine, that is features. So training can be slow, but accuracy is high. Training, why training is slow? Because the mathematical computation for higher dimensional space. So and when we convert lower dimension to higher dimension, so complexity is higher. So when we maximize the margin for a complex nonlinear data, that will be very slow. So used for both classification as well as regression estimation, and very effective in many large practical problems, and only work with real numbers. So we have to convert the real number into the if we have some categorical value, then we have to convert that categorical value into real number for performing support vector machine classification. So this is not suitable for large database, and not work with the overlapping classes. And some other issue, SVM works just I says that this work only real valued space, and for a categorical attribute we need to convert its categorical values to numeric values. And hyperplane produced by support vector machine is hard to understand by human users. So if your problem involves the human user, that support vector machine is commonly used in applications that do not require human understanding. So this is mainly theoretical concept. Thank you.
Okay, so if anyone have any question, you can ask.
Sir,
Okay.
I have a question. I mean,
Yes,
query.
yes. Yeah.
Yes, yes.
Sir, that means if we choose a particular kernel, then we can set the parameters and check which parameters is performing better. But which kernel to choose, there is no rule, right? And
Yes.
for a particular problem, I mean, we need to try then all the kernels.
All the kernel and by try and see method.
Okay.
So because kernels have their own functionalities, some used in image classification, some in text classification, and some in deep learning. So mainly for text classification, you can
Depending upon
for
the
different-
usage, you can choose, na?
yes, yes.
Okay.
That is there is no fixed rule.
Okay, sir. Okay. Thank you.
Okay, thank you so much. And any other question? Actually, we are running out of time, so we cannot take that question. Any questions?
Yes, actually,
So-
the topic is very lengthy, so I just finish quickly in the last.
Yeah, I can understand. Well, I would like to thank our speaker, Dr. Dhananjoy Bhakta, for such an informative lecture. And I thank our HOD and Dr. Devhoti Mishra for providing us such a good platform where we can arrange as well as attend the lecture series. I'd also like to thank the organizing committee, that is Dr. Madhuri Rao and Dr. Sharda sir, Dr. Divya Bandhu sir, okay, for their supports. And finally, I would like to thank our participants for their participation, because without their participation, this lecture series cannot be done successfully. So I'd like to thank all of you, and thank the CSC department and SOA University for providing us such a wonderful platform for sharing our knowledges. And thank you, sir. Thank you all.
Thank you.
So that's all. We can leave now. Anyone?
Okay, thank you.
Okay. Sir.